everyone. Subject ME 8492 Kinematics of Machinery, 5th unit, Friction in Machine Elements. In this 5th unit we are going to see about the belt and rope drives. The belt or rope are used to transmit power from one shaft to another by means of a pulley which rotate at the same speed or at the different speed. The amount of power transmitted depends upon the following factors. That is the velocity of the belt, tension under which the belt is placed on the pulley, the arc of contact between the belt and the smaller pulley, the condition under which the belt is used. It may be as the shaft should be properly in line to ensure the uniform tension across the belt section, and these are the various conditions under the belt is used. A long belt tends to swing from side to side, causing the belt to run out of the pulley, which in turn develops the crooked spot in the belt. The tight side of the belt should be at the bottom, so that the whatever sag is present on the loose side will increase the arc of the contact of the pulley. In order to obtain the good result with the flat belt, the maximum distance between the shaft should not exceed 10 meters and the minimum should not be less than 3.5 times the diameter of the larger pulley. And the next topic is the selection of belt drive. The various important factors upon the selection of belt drive depends on speed of the driving and the driven shaft, speed reduction ratio, power to be transmitted, center distance between the shaft, positive drive requirements, shaft layout, space available, service conditions. These are all the various factors for selecting the belt drive. And the next topic is the types of belt drives. There are 3 different types based on light drives, medium drives, heavy drives. In light drives, used to transmit the small power at a belt speed up to 10 meter per second. It is applicable in the agricultural machines and small machines tools. And the next drive is the medium belt drive. These drives are used to transmit medium power at a belt speed over 10 meter per second up to 22 meter per second. These drives are used in machine tools. And the final belt drive is the heavy drives. These are used to transmit the large power at a belt speed above 22 meter per second, as used in the compressor and generator drives. Next is the types of belt. Mostly 3 types of belt: fat belt, V belt, circular belt. Fat belt is mostly used in the factories and workshops, where a moderate amount of power is to be transmitted from one pulley to another when the 2 pulleys are not more than 8 meters apart for flat belt drive. And second is the V belt. Is mostly used in the factories and workshops, where a moderate amount of power is to be transmitted from one pulley to another when the 2 pulleys are very nearer to each other. For V belt, the 2 pulleys are very nearer to each other. And the third type is the circular belt or rope. It is mostly used in factories, where a great amount of power is to be transmitted from one pulley to another when the 2 pulleys are more than 8 meters apart. And the next one is what are the materials used for belts. These are the three types of belt: flat belt, V belt, and circular belt. The next thing is the various types of materials used for belts. The first one is the leather material, fabric and cotton material, a rubber belt. These are all the different types of material used for manufacturing the belt. First, leather belt is the most important material for making the leather belt. The best leather belt are made from 1.2 meter to 1.5 meter long. The strips cut from either side of the backbone of the top grade stirrups. The hide side of the belt should be in contact with the pulley. This gives a more intimate contact between the belt and the pulley and place the greatest tensile strength of the belt section on the outside for the maximum in tensions as the belt passes over the pulley. For leather belts, single layer and multi-layer leather belts. The second type is the in leather belts, the leather belt must be periodically cleaned and dressed with a compound or dressing containing needs of food and or other suitable oil so that the belt will remain soft and flexible. The next one is the cotton or fabric belt. Most of the fabric belts are made by folding, canvassing or cotton duck to 3 or more layers depending upon the thickness desired and stitching together. These belts are woven also into a strip of desired width and thickness. The cotton belts require little attention, therefore these belts are mostly used in the farm machinery and belt conveyors. The next material is the rubber belt. These belts are made of layer of fabric impregnated with a rubber composition and have a thin layer of rubber on the faces. These belts are very flexible but are quickly destroyed if allowed to come into contact with the heat, oil and greases. One of the principal advantages of these belts is that they may be easily made endless. These belts are found suitable for sawmills, paper mills, and the next one is the types of flat belt drives: open belt drive, cross belt drive, quarter turn belt drive. These are all the different types of flat belt drives. First one is the open belt drive. See the diagrams. A driver A and the driven B is connected by the flat belt LMQR. The open belt drive is used with the shaft arranged parallel and rotating in the same direction. In this case, the driver A pulls the belt from one side and delivers to the other side. Thus, the tension in the lower side belt will be more than the upper side belt. The lower side belt is known as the tight side. The upper side is known as the slack side. Next one is the cross belt drive. See the diagram. Driver A and driven B. The cross or twisted belt drive is used with shaft arranged parallel and rotation in the opposite direction. In open belt drive, shafts are arranged in parallel and rotating the same direction, but in cross belt drive, rotate the a driven shaft in opposite direction. The driver pulls the belt from one side and delivers to the another side. Thus, the tension in the belt RQ will be more than the belt in the LM side. So, which one is the RQ is the tight side, and belt in the LM side is the slack side. The next one is the quarter turn belt drive. It's also known as the right angle belt drive, as shown in this figure. Yeah, a right angle belt drive or quarter turn belt drive is used with the shaft arranged at right angles and rotating in one definite directions in order to prevent the belt from leaving the pulley. The width of the face of the pulley should be greater or equal to 1.4 width of the belt. The next one is the belt drive with the idler pulley. In between the driver and the driven, the idler pulley is used. Show this diagram. Belt drive with the single idler pulley and a belt drive with the many idler pulley. The idler pulley used with the shaft arranged parallel, and when an open belt drive cannot be used due to the small angle of the contact on the smaller pulley. This type of drive is provided to obtain the high velocity ratio, and when the required belt tension cannot be obtained by other means. The next one is the compound belt drive. Is used when power is transmitted from one shaft to the another shaft through a number of pulleys. The diagram shows that the power is transmitted from one shaft to the another through a number of pulleys. The diagram shows the driver 1 and is the send in between the driver and the driven, a compound drive. And the next drive is the stepped cone drive. Diagram shows the stepped cone drive. A stepped cone pulley drive is used to change the speed of the driven shaft while the main or driving shaft runs at a constant speed. This is accomplished by shifting the belt from one part of the step to the other. The next one is the fast and loose pulley drive. The fast and loose pulley drive is used when the driver or machine shaft is used to started or stopped whenever desired without interfering with the driving shaft. The pulley which is keyed to the machine shaft is called fast pulley and runs at the same speed as that of the machine shaft. A loose pulley runs freely over the machine shaft and is incapable of transmitting any power. When the driven shaft is required to stop, the belt is pushed on the loose pulley by means of the sliding bar. The diagram shows that fast and loose pulley drive. And the next one is the velocity ratio of the belt drive. Velocity ratio. It is the ratio between the velocity of the driver and the follower. It may be expressed by mathematically. N2 divided by N1 is equal to D1 divided by D2, where D1 and D2 are the diameter of the driver and the follower. N1 and N2 are the speed in the driver in RPM, and N2 is the speed in the follower in RPM. Follower or driven. The length of the belt that passes over the driver in 1 minute is equal to pi into D1 into N1. Similarly, the length of the belt over the follower in 1 minute, that is pi into D2 into N2. Since the length of the belt passes over the driver in 1 minute is equal to the length of the belt that passes over the follower in 1 minute, therefore pi d1 n1 is equal to pi d2 n2. The velocity ratio is equal to n2 divided by n1 is equal to d1 divided by d2. When the thickness of the belt T is considered, then the velocity ratio is equal to n2 divided by n1 is equal to d1 plus t divided by d2 plus t. You know that the velocity v is equal to pi dn divided by 60 meter per seconds, but the peripheral velocity of the belt on the driven or follower pulley is equal to v2 pi d2 n2 divided by 60 meter per second. When considering the slip and without considering the slip, when there is the no slip, then v1 is equal to v2. v1 is the velocity of the belt in the driving pulley, v2 is the velocity of the belt in the driven pulley. Now consider v1 is equal to v2, pi d1 n1 divided by 60 is equal to pi d2 n2 divided by 60. By equating this, n2 divided by n1 is equal to d1 divided by d2. Next, velocity ratio of the compound belt drive. Now we are discussing the velocity ratio of the compound belt drive. Sometimes the power is transmitted from one shaft to the another through the number of pulleys. We already see the compound belt drive. The pulley 1 driving the pulley 2, since the pulley 2 and 3 are keyed to be the same shaft, therefore the pulley 1 also drives the pulley 3, which in turn drives the pulley 4. We already see the compound belt drive. This shows that d1 is the diameter of the pulley 1, n1 is the speed of the pulley 1, and d2, d3, d4 are corresponding values of the pulleys, diameter of the pulleys, and n2, n3, n4 are the corresponding values of the pulley, speed of the pulley of second, third and fourth pulley. We know that the velocity ratio n2 divided by n1, for considering the pulley 1 and 2, n2 divided by n1 is equal to d1 divided by d2. Fix it as the equation number 1. Similarly, the velocity ratio of the third and fourth pulley, n4 divided by n3 is equal to d3 divided by d4. It is the equation number 2. Multiplying the equation 1 and 2, we get n4 divided by n1 is equal to d1 into d3 divided by d2 into d4. A little consideration will show that if these are 6 pulleys, n6 divided by n1, that is speed of the last driven divided by the speed of the first driver is equal to the product of diameter of the drivers divided by the product of diameter of the drivens. That is, and the last driven, the speed of the last driven n6 divided by the speed of the first driver n1 is equal to d1 d3 d5, the product of d1 d3 d5 divided by the product of d2 d4 and d6 is the diameter of the driver divided by the driven pulleys. The next one is the slip in the belt, slip of the belt. I have discussed the motions of the belt and shaft assuming the frictional grip between the belt and the shaft, but sometimes the frictional grip becomes insufficient. This may cause some forward motion of the driver without carrying the belt within it. This may also cause some forward motion of the belt without carrying the driven pulley with it. This is called slip of the belt. and is generally expressed as a percentage. As a result of the belt slippage is to reduce the velocity ratio of the system, as the slipping of the belt is common phenomenon. Thus the belt should never be used where a definite velocity ratio are of importance. Let S1 percentage is equal to the slip between the driver and the belt, and S2 percentage, slip 2 percentage is equal to the slip between the belt and the follower. The velocity of the belt passing over the driver per second. Velocity of the belt V is equal to pi d1 n1 divided by 60 minus passing over the driver per second. Pi d1 n1 by 60 into S1 divided by 100. Here, by solving this equation, V is equal to pi d1 n1 divided by 60, 1 minus S1 divided by 100. That is equation number 1. And the velocity of the belt passing over the follower per second. Pi d2 n2 divided by 60 is equal to V 1 minus S2 divided by 100. Substituting these equations, we are getting the n2 divided by n1 is equal to d1 divided by d2 into 1 minus S1 by 100 minus S2 by 100. For neglecting S1 and S2, where S1 plus S2 is the total percentage of the slip. So N2 divided by N1 is equal to D1 divided by D2 1 minus S divided by 100. If the thickness of the belt T is considered, then N2 divided by N1 is equal to D1 plus T divided by D2 plus T into 1 minus S by 100. Next we are going to see the exercise in the belt drives. Exercise number 1. An engine running at 150 rpm drives a line shaft by means of a belt. The engine pulley is 750 mm diameter and the pulley on the line shaft being 450 mm. A 900 mm diameter pulley on the line shaft drives a 150 mm diameter pulley keyed to a dynamo shaft. We have to find the speed of the dynamo shaft. Conditions for finding the speed of the dynamo shaft. And the first one is that there is a no slip, and considering the 2% of slip at each drive. So this is problem. We have to find the speed of the dynamo shaft. So the pictures show the 750 mm engine shaft. In between that line shaft of 450 mm, it's a compound drive, and the same shaft, line shaft, having 900 mm pulley that transmit the dynamo shaft of 150 mm dia. So the final speed of the dynamometer shaft. First we are considering the no slip. We know that slip percentage N4, the final speed is the N4. N4 by N1 is equal to D1 into D3 divided by D2 into D4. Substituting these values, known values, N4 is equal to 1500 rpm. There is no slip occurred. And second condition, when there is a slip of 2% at each drive, the same formula. When considering the slip, N4 divided by N1 is equal to D1 into D3 divided by D2 into D4 into 1 minus S1 divided by 100 into 1 minus S2 divided by 100. Substituting these values, and S1 and S2 is the 2%, and finally we get N4 is equal to 1440 rpm. Solution for this problem: when considering the slip, the speed of the dynamo shaft is 1440 rpm. Without considering the slip, there is no slip, the speed of the dynamometer shaft is 1500 rpm. Next, creep of belt. When the belt passes from the slack side to the tight side, a certain portion of the belt extends and it contracts again when the belt passes from the tight side of the slack side, to the slack side. Due to these changes of the length, there is a relative motion between the belt and the pulley surfaces. The relative motion is termed as the creep. The total effect of creep is to reduce slightly the speed of the driven pulley or the follower. Considering the creep, the velocity ratio is given by n2 divided by n1 is equal to d1 divided by d2 into e plus square root of sigma 2 divided by e plus square root of sigma 1, where sigma 1 and sigma 2 are the stresses in the belt on the tight and the slack side respectively. E is the Young's modulus for the material of the belt. Next, we are going to see the problem based on creep in the belt. The power is transmitted from a belt from a pulley 1 meter diameter running at 200 rpm to a pulley 2.25 meter dia by means of a belt. Find the speed lost by the driven pulley as a result of creep. If the stress on the tight and the slack side of the belt is 1.4 megapascal and 0.5 megapascal respectively, the Young's modulus of the material of the belt is 100 megapascal. Solution. Write the given details. The diameter 1 and diameter 2 and stresses and Young's modulus given values. Let n2 is the speed of the driven pulley, and neglecting the creep, we know that n2 divided by n1 is equal to d1 divided by d2. For rewriting this formula, n2 is equal to n1 into d1 divided by d2. Substitute these values. We have to find the n2 speed of the driven pulley 88.9 rpm. Now considering the creep, n2 divided by n1 is equal to d1 divided by d2 into e plus square root of sigma 2 divided by e plus square root of sigma 1. Substituting these values, we have to find the n2, that is speed of the driven pulley. n2 is equal to 88.7 rpm. Now the speed lost by the driven pulley due to the creep, that is neglecting the creep, speed minus the considering the creep, 88.9 minus 88.7, that gives the 0.2 rpm. That is the speed lost by the driven pulley as a result of creep is 0.2 rpm. Due to creep, 0.2 rpm will be reduced, speed will be reduced. And next one is, we are going to see the length of an open belt drive. How to find out the length of an open belt drive? See the diagram. The length of an open belt drive. Here the driver and the driven pulleys O1 and O2. We have already discussed in the previous chapter about the open belt drive. R1 and here this pictures, R1 and R2 are the radius of the larger and the smaller pulley. X is the distance between the center of the pulleys, that is O1 and O2, and the length of the belt is equal to L. Let the belt leaves the larger pulley at E. The belt leaves the larger pulley at E and G, and the smaller pulley at F and H. The belt leaves the smaller pulley at F and H as shown in this figure. From the geometry of the figures, we find that the O2M will be perpendicular to O1E. So let the angle MO2O1 is equal to alpha radians. We know that the length of the belt, that is capital L is equal to that is arc of JGE plus EF plus arc of FKH plus HG. That is the twice of L is equal to twice of arc of JE plus EF plus arc of FK. Considering this is an equation number 1. From the geometry of the given figures, we know that the sin alpha is equal to O1M divided by O1 into O2. So R1 minus R2 is divided by X. Since alpha is very small, therefore putting sin alpha is equal to R1 minus R2 divided by X. It is considering as the equation number 2. Rj is equal to R1 into pi by 2 plus alpha. Now solving this equations 1 and 2, 3, 4, we get the EF is equal to X minus R1 minus R2 the whole square divided by 2X. Is equation number 5. Substituting the values of equations 1, 2, 3, 4 in this form, we are getting the length of the belt L is equal to pi R1 plus R2 plus 2 alpha into R1 minus R2 plus 2x minus R1 minus R2 the whole square divided by X. In terms of fully radii, L is equal to pi into R1 plus R2 plus 2x plus R1 minus R2 the whole square divided by X. In terms of fully diameter, pi by 2 d1 plus d2 plus 2x d1 minus d2 the whole square divided by 4x. Next, let's see the problem in length of the belt. A shaft which rotates at a speed of 160 rpm is connected by belting to a parallel shaft 720 mm apart, which has to run at 60, 80 and 100 rpm respectively. The smallest pulley on the driving shaft is 40 mm in radius. Determine the remaining radii of the two-stepped pulley for first condition cross belt drive and the second and an open belt, neglecting the belt thickness and creep. Write down the given details. That is the speed N1 is equal to N3 is equal to N5 is equal to 160 rpm and distance between the shaft X is equal to 720 mm and N2 60 rpm, N4 80 rpm, N6 100 rpm and R1 is equal to 40. The diagram will show the clear details. Yeah, the driving shaft 135 and the driven shaft 246 having the different types of radii and the distance between the two axes is 720 mm. Let us see the answers. For a cross belt, we know that the pulley 1 and 2, N2 divided by N1 is equal to R1 divided by R2. So we know that the N1 and N2 speed of the pulleys. So you have to find the R2 radius 2 is equal to 106.7 mm. For pulley 3 and 4, N4 divided by N3 is equal to R3 divided by R4. Here we are going to relate the radii, that is N4 divided by N3 is equal to twice of R3. We know that the cross belt drive R1 plus R2 is equal to R3 plus R4, that is equal to R5 plus R6. that is 146.7 mm. Substituting these values in 2 or 3, that is n4 divided by n3 is equal to r3 into 160 divided by 80, that gives 2 r3. So r3 plus 2 r3 is equal to 146. In this equation we have to find the r3, that is radius of the third stepped pulley is equal to r3 is 48.9 mm and r4 is equal to 97.8 mm. Now for the pulley 5 and 6, the same way, n6 divided by n5 is equal to r5 divided by r6. Into the relations, r5 into 160 by 100 is equal to 1.6 r5. From equations 1 we are going to solve it for finding the radius 5, that is 56.4 mm and r6 is equal to 90.2 mm. It is for, you have to find the cross belt drive radius of r2, r3, r4, r5 and r6. Now we are going to see about the this radius for open belt conditions. In open belt conditions, for pulley 1 and 2, n2 divided by n1 is equal to r1 divided by r2. In these relations we have to find out the radius 2, r2 is equal to 106.7 mm, and the pulley for third and fourth pulley, n4 divided by n3 is equal to r3 divided by r4. In the meanwhile, r4 is equal to 2 into r3. We know that the length of the belt for an open belt drive, L is equal to pi into r1 plus r2 plus r2 minus r1 the whole square divided by x plus 2x. By solving these known values for finding the length of the belt, L is equal to 1907 mm. Since the length of the belt in open belt is constant, therefore the pulleys 3 and 4, the length of the belt L is equal to, length is already known, 1907 is equal to pi r3 plus r4 plus r4 minus r3 the whole square divided by x plus 2x. In this equation we are going to find about the r3 by solving this given values. To find out the r3 is equal to 49.3 mm and r4 is equal to 98.6 mm. Now for the pulley 5 and 6, for getting the r5 and r6 radii of the pulley, n6 divided by n5 is equal to r5 divided by r6. By solving this equation we are getting 1.6 r5. By solving this given things in the length of the belt, by solving the equations length of the belt and the speed of the 5th and 6th pulley, so r5 is equal to 60 mm and r6 is equal to 96 mm respectively. Thank you.